Hey everybody, this is Larry. This is me going Q4 of the weekly contest 443 minimum operations to make elements within K subarrays equal. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think about this one. This one I actually mostly solved in two ways, even though the other way took me a long time, and I'll go with that way just as a bonus, but I'll go with that thing second, even though I did that first live. But yeah, this one I feel a little bit sad. I should have gotten it, but I was not even close because I was just missing a little bit thing. One is just that I was trying to use heaps instead of sorted list, and the hard part about that is that there's no removal in heap, and that kind of made things tricky for a median, right? So in this problem, the key thing is that there's a sliding median. You have to figure out how to do a sliding median, and this is probably going to be a long video. Let me bring up the drawing board. Long video because there's a lot of drawing. But yeah. So basically, well, okay. So the thing about this is that there's another component, right? Which is that, okay, given a section of numbers, what number should we convert it to? Like, okay, so because we're given x, which is the number of items that we're considering, and in that window we want to minimize the number of operations, right? So how would that happen? Well, the way that happens is with a median, right? And the reason is because, okay, you can think about a number as, and let's say you have a list of number and it's sorted, just to kind of go over it a little, just to illustrate it a little bit better, and kind of actually ties into this problem very well, right? So here, right, and you're trying to find a number in which they all are the same, right? And to minimize the number of change. Well, the answer is for even numbers, it's going to be any number between 7 and 10. And for here, you can just choose 7 because it could be any number from 7 to 10, and 7 is within 7 and 10. And the reason is because you can think about this as, okay, there these numbers to the left and these numbers to the right, right? So that means that, let's say, with an exchange argument, let's say that you're trying 6, right? So you moved, you think 7 is good, but you want to try 6, right? Well, 6 means that there are 4 numbers to the right that will get a +1, right? Because it's farther away. So that means that you have +1 to whatever answer you had previously. While two numbers to the left will get -1 because closer. But as a result, this gives you a net +2 because there are more numbers to the right, right? And here, in the same way, we go 8. Well, 8 is fine because on the left there's 3 -1s. Oh, sorry, in this case we're going right. So there's 3 +1s, but on the left, on the right, there are 3 -1s, right? -1. So that's why 8 is okay as well, because they cancel out to be 0, right? So you could play around with this idea, but that's the exchange argument of, okay, if you're given a median and you go left, it's going to cost you more. You go right, it may cost you more, it may not. The only reason is because this is even number of elements, so 7 and 10 is fine. And if you go past 10, you can even prove that, right? So if it's 11, well, we have 4 numbers to the left going 4 + 1, and 2 numbers going -1, so that's too much, right? And you can also try with odd number of elements, right? So let's say we have a 9, right? 9 here. If you try 8 now, going 8 this way, you have 3 numbers to the right, 3 numbers to the left. So, oh, no, sorry. You have 3 numbers on the left that is closer for -1, but you have 4 numbers that's +1, including the 9, right? So that's why the median is what you want for this problem. Okay, so as a result of that, then now, you're trying to figure out this rolling median. And the way to do a rolling median, there are a couple of ways to do it, but honestly, I kind of messed up with this one. Initially, I did have this heap idea, but the thing with heaps in Python is that you cannot remove them from the heap, right? You have to do a lazy removal thing. And I didn't think of it that way, and I did end up using a median, using a sorted list, which is fine, but it was not I was using one sorted list to do the median, which is fine, but it didn't let me do like the cost, right? Because one thing is that if you have the median, so you have a sliding window, and you have a median, then if you want to change the median, you still have to get the cost of everything, right? So if you're going to calculate the entire cost matrix for the entire array, that's going to be n squared, right? Or n times x, but x can be n, so it's going to be really slow for you, right? So that's kind of the one of the difficulties, right? So the key, but the two heap ideas is basically the way that you want to do it. The thing is that, at least in Python, and I'm talking Python specific, is that you want to use two sorted lists for heaps. And the idea behind the two heap median solution is actually kind of well known. It's just that you have a heap to the left. Oops. You have a heap to the left and you have a heap to the right, right? So you maybe have, let's say, I don't know why I drew it like a stack. How do you draw a heap? Whatever, right? So we have like, so say 8, right? And then on the right side, you have 9, 10, 11, 15, something like that. So basically, you put all the numbers that are smaller than on the left and smaller on the right. And basically, the invariant here is, there are a couple, but let's just say for even numbers for now. If they're even numbers, then there are the same number of elements to the left and same numbers of elements to the right. And then you could pick the top of the stack, I don't know, to the left. It doesn't really matter. Like, as long as you know what you're doing and consistent. There are a lot of variations, but they always have a similar idea, right? But the way that I would do it is that, okay, so if it's even, then you pick this one as your median, and so forth. And the variant is that if you add numbers, let's say you add a 12, well, you add a 12, and then that means that, well, the right is too big, so then now you move the 9 to the left side, right? And then later you remove a 10, and then you move the 9 back to here, right? Or something like that. So then now you have 4 numbers on the left and 4 numbers on the right, right? Yeah, and then that's basically it. And it turns out from this, you could get the cost very easily. This is the one thing that I kind of, I had all the components, but honestly, I just wasn't able to put them together because I was thinking about the heap solution, but I wasn't thinking about the heap using sorted list. But now that you have this, then it becomes a little bit easier. And why is that? Because you can keep track of this left sum, and you can keep track of right sum. Why does that help? Because then now you could get the cost from median very easily. This is the part that I've always known, and I was actually even trying to do this for my other solution, but I couldn't get it quite right without something crazy, which I'll show in a second. But let's say you have, okay, so let's say you have, so now we, let's say we have this number, right? 3, 8, 9, 10, 11, 12, right? So these are our numbers. And here, again, the median is going to be 9 or 8, sorry. So let's just draw a line. All right, let me draw a different color line, right? So this is the left heap, this is the right heap, right? So, and I'm going to say heap, but implementation-wise, it's going to be a sorted list. And then the idea is that, and you can actually, yeah. So the idea here is that because you now separate them into 2 parts, it actually becomes easy to calculate. The logic that I always think about is just visualization. And the visualization is that I just draw it out. So here we have the number 1, right? 1 height. We have 2, we have the 3, and then we have the 8, something like this, right? And now we know that the median is 8. So what does that mean? That means that we want to draw an 8 here, right? That means that we're trying to find out what the total of this gap, right? And then how do I do that? Well, so it turns out the way to think about this is just by drawing a rectangle. And we draw a rectangle, well, you know the width, or I guess this is the length, which is the number of elements, and you know the height, which is whatever you want the median to be. So now you know the area of the rectangle. And then now you're trying to get the sum of this thing, which is, I suppose, the area of the green. It's not a rectangle, but you know, green whatever this is, right? And the green whatever this is just the red rectangle subtract by the black sum, right? I don't know why I'm drawing it again. So this subtracted from this gives you the green part, and that's how you do this part. Without loss of generality, I implore you in home to do it for this for the right side, and that's really it. Having this visualization is everything you need, and even though I didn't know all this stuff, today I just wasn't able to put them together implementation wise. I mean, I was able to do it another way, honestly, using segment tree. We'll go with that in the future, but for now, this is basically the idea. And the reason why you need this separation is because, and this is the part that I got stuck on for a long time, honestly, is that I knew that I had something similar, but because I was using one sorted list to begin with, the problem was that I had something like, let's say you have 1, 2, 3, 8, 9, 10, okay, right? 11 and 12. So then here, when I was trying to draw a line for this, I just couldn't figure out how to make sense of it. How to get this and this at the same time, right? So I didn't know how to get that at the same time, the area of this area, because these have the same signs and stuff like that. But it turns out if you separate them out by 2, that's how you solve it. And it turns out that that's the same with the heap structure. And I just didn't do it that way. Okay, so let's go over the code. That is the idea. You should be able to solve this with this idea. I believe in you, at least in the data structure. So okay, so I have a rolling median. Let's go over it. So I have a left side, left sum as we talked about, so that we could do the subtraction. Right side, right sum. You'll see in a second if you haven't solved it already. I don't think I used median. I used it earlier on, but I didn't. And size is just the size of the window that we keep track of. Yeah. In fact, I don't think we need any of this anymore. I forgot to erase them out. But because I thought I might, but let me double check that does this work real quick. I remember after the right before I submitted, I was like, all right, let's leave it in just to see if it works, and then we'll remove it. But I forgot to, so that's okay, right? So yeah, so you don't need it. But the idea here is that okay, on add. If the add is, well, if there's no element on the left side, we put it on the left side. If the biggest element on the left side is bigger than or equal to add, the element you're adding, then we just put on the left side, right? Because we know that it'll be inside there somewhere. And then now we do the same for the right side. If it's not on the left, then it's on the right. And then after that, we call a balance function, right? Same thing on remove. Remember, we keep track of the sum on the left side and the right side, and the same thing with remove, right? If it's on the left, we remove it from the left, we subtract it from sum. If it's on the right, then we remove from the right, and we remove from the sum. Balance is the hard part. And also I realized that I focused on the rolling medium, but I did not go over the dynamic programming part. So we'll go over that afterwards with visualization anyway. But yeah, balance is, yeah, basically if there's too many elements on the left, we move it from left to right, left to right. If there are too many elements to the right, we move it from right to left, right? That's it. And then afterwards, we calculate the new median, which is always going to be the biggest element on the left side. The reason why is because the invariant that I had is that they're either the same size, the left and right, and if they're not, then the left one will be bigger than the right one by 1. So in that case, that'll be on the left side. So that's why I said this way. And then the cost is just the left cost, which we showed and visualized, and then the right cost, which we didn't visualize, but hopefully you visualized at home. But that's basically how I did it, right? So this is the sum of both things minus the rectangle. You could draw it out. And yeah, And then now we have all the cost, and that's it. This is all. So did I need prefix sum? Oh, I need the prefix sum to do it another way, but I think this way I didn't need it anymore. But yeah, so this is to get all the cost, right? So this is pretty straightforward sliding window stuff. We slide on the right, we add it to the median. If the window to the left can be removed, we remove it from the left. Otherwise, we set up the cost, which is the updated cost which we have here, right? And that's it. And then now the rest is DP, and the DP is actually not that bad either, but it also could be tricky. But this part, honestly, Leetcode has shown similar problems. I don't know if it's recently, but recently-ish, so that's why I haven't done it. But the idea here is that, okay, so now let's say you have a cost array, right? Basically, you have some, I don't know, I'm gonna, these numbers are fake, so don't, because I'm too lazy to calculate them out, so don't hold me to them or whatever, right? I don't know, I'm just writing random numbers anyway, right? And then now let's say the cost function is going to be, here there's some cost, right? I don't know what the cost is, so I'm just going to write out a random number, so don't hold me to this. Let's say this is 12, this is 15, this is 9 or whatever, right? So then here, instead of writing it like that, I would just have a different cost array that maps, because everything is fixed, right? So we can actually write a sub array that's smaller, and we're doing size 4, then this is just 12, 15, 9, I don't know, and then you just keep on going, right? Like I said, I'm just putting in random numbers, but yeah, right? And this is the cost of jumping from here to here, for example, right? And this is the cost from jumping to here to here. And as you can tell, this is just dynamic programming, right? Because at this part today, I'm not gonna go over that deeply, honestly. But yeah, the key thing to note is that K, we have to have at least K non-overlapping ones, but we're trying to minimize, so we're always going to do exactly K, right? Because it doesn't make sense to do K plus 1 because it just requires more operations. So you want exactly K. And then the other thing to notice is that K is 15. Since K is 15, you're able to do a K times NDP, and that's basically really it, as long as you have it. And this is my K times NDP, right? Is that okay? And yeah, you could say it out loud. I think sometimes it's easier, which is that, okay, so if you have, so this is basically tick no tick, right? So no tick is just getting the previous element, right? Skipping to the previous element, and you don't take a path. This is tick, so let me write it down actually. No tick, right? So this is no tick, so we don't use one of the J's, or we don't use one of the overlaps that we have to use. If we do, then this is tick, right? If we do, then we just compare this to the shortest path, J minus 1 ago, so K minus 1 ago, and also this is the length of the jump, right? And this is the cost of the jump. So this is standard dynamic programming stuff. I have crazy allergies. I have trouble talking and breathing at the same time, honestly. So my apologies if I'm cutting it a little bit short today. But that's basically it for this particular part. And then we just minimize the thing over all indexes, which is dp sub k of n, right? Because we need at least k, and then it's just whether it ends at 0, and it ends at 1, it ends at 2, ends at 3, ... and it takes the minimum of them. And that's it. Yeah, this is going to be, so each median, and it takes, let's go with complexity. So this takes 2 log n operations at most, well actually 1 at most really, but 2 of them here, 2 log n here, log n here, log n here. Keep in mind that even though this is a while loop, you cannot have more than 1 element on the other side, right? Like it can be only imbalanced by like 1 or 2 elements, so it will only loop once or twice maybe. So yeah, and obviously both of them are mutually exclusive. So yeah. So this is still log n. So yeah, so we have n times log n times log, well, not, but two log n operations. So this is just n log n loop. And this dp is n times k, right? And that's it. Yeah. So the bonus upsolve that I did, except I did this first, it took a while, is by, not this one, is this one with a sparse segment tree. So this is a really ridiculous long code. You could watch me solve it live actually, but without deep explanation, it is the same idea, except for that I implement from scratch actually a sparse segment tree, which I'm really happy about, honestly, because I've never done a sparse segment tree by myself, but it's just too slow for this problem, so that's why I had to rewrite it. But yeah, and you can watch it live. But basically the idea here is that the sparse segment tree, this particular one, has it keeps, the way that I think about it is that it keeps track of some f sub x is equal to k, where we have k copies of x, and so this is what we increment and keep track of, and then it also answers the query. So this is the update increment, and then the query is get sum between a and b. So basically and a is the key, right? Meaning basically, for example, if we have, sorry, struggle breathing, it's really tough. But yeah, it's just basically, for example, if you have 3 and a 6 inside, maybe even add more numbers. So we have 2 3s, you have 6, 7, and 8. I'm writing out a waveform. So if you query for say between 3 and 7, then now this sums up all the 3s and all the numbers between 3 and 7 together. So that's basically how I implement this. And everything is just divide and conquer. We have increment, where you have a binary searchy thing. We have a node class for the segment, and this basically creates the tree downwards. So that this makes increment log n, right? And then we propagate the results back up. It's a very expensive log n because we wrote it in Python, and there are not a lot of nodes, and we start with 10 to the 6, so it's like 25 depth or something. Or maybe not 25, maybe like 20 plus some around there, so like 21, 22 maybe. But yeah, and then query is just we sum up all the components to get between a range, and you can kind of go through it. I'm going to show you this code. So this is the node, this is the sparse segment tree, and this is the query. Keep in mind that I'm not going to go over this in detail. It's just, but this is correct. I solved it in another way. But yeah, and this is the query. I was trying to optimize it by not doing recursion, which is why this looks a little bit awkward. But basically, it just goes through left, goes through right, and then recurse all those pieces together. And the reason why this is log n is because every piece is going to be the biggest, and there's only log n pieces that sums up to the L and R. But yeah. And then this whole code, the DP is exactly the same. I think I didn't even change it because this works. So I copied it for the good solution pretty much. And this is the thing that we were doing. And the idea is like that, but it's very tough. So I have the sparse segment tree, I have a sorted list, I keep track of the last median, I keep track of total delta for the solution as the rolling cost, and this is the cost array that we also had, right? But yeah, but basically, when I add a median, add a number to the median, to the sorted list, and then I increment that count of that number by 1, right? So this is to slide into the window, and then I just keep track of how much delta it adds to the compared to last median, right? Yeah. And then we also, on the left side, do the same thing. We remove it from the sparse tree, and then we update total delta as well, right? Because the last median changed. And yeah, and then there's just a bunch of stuff. So if the median is size, that means that we finally have enough elements to do the median. Let's do it for the first time, right? So this just calculates the median. This is pretty straightforward because we're doing it for the first time. But then now the other one is we have 3 cases, which is, I don't know. I'm not happy about this, but it is what it is. But basically, I divide the numbers into 3 categories, right? We have the median, the biggest, which means that, so M is bigger than last median. So you have M, you have last median, right? And then you have numbers on top. The numbers on top, you're going from last median to median. So then you for each number, you make up the gap there. That's what this thing does, because we got bigger, so it gets closer to the biggest one. And the same thing with the smallest is that you, given this thing, this is the smallest here. So then now those numbers get farther away, right? As you go from last median to median. And then the middle is the tricky part. And basically the idea here is that given the middle, we're just trying to get the sum and then just wrap them around this way. You can work this out. This is actually a similar idea than before. But yeah. But now that I think about it, I think I don't even need to do all this craziness. You can think about this as also, yeah, and this is just the other case, right? So M is less than median, I do the same thing. And that's it. It's just about keeping track of these things. And the idea behind this particular part is the same thing that we talked about, except for now we get the area inside the middle, right? Maybe I'll draw it real quick, actually. I don't know that this is, I mean, I don't know. I don't know if this is useful, but it's interesting to me anyway. But basically, yeah, as I was saying, let's say we have, you know, so, yeah, so we have, so we're going from last median, let's go L to M, so we're going to here, right, this direction. And then the smallest numbers, we can kind of count the number of them, right? And all of them, it doesn't matter. It's just going to go, you know, whatever it is. And remember that the previous delta, we already calculate them. So we already calculated to here. So then now we just have to close this gap. So that was part of it, right? And then the other one is that we have really big numbers, right? Something like that. And they're all sorted. So something like that, right? And keeping in mind that so previously we already subtracted out from down under, right? So that means that we have actually, no, it's, so it's actually right? So something like that, right? And yeah, and basically we had the entire red area calculated before, but now we want to subtract out this thing, and that's basically what the other part of the code does, right? So then now the middle part is just, well, we have this thing like this, something like that, right? And previously we have this thing, right? Let me change the color actually. So previously we have this thing, right, calculated, because that was over the old median, which is here, right? So then now we're trying to figure out the yellow, which I'll, maybe not yellow, the other cyan. Right now we're trying to figure out this part, and so yeah, and the formula is just so that we could get this part and then convert it into this part. So that's what all this long code does from this graphic, and that's what the sparse tree enables us to do, is that I'm now able to get the left and the right in that way. But now that I think about it, I think, especially knowing what I know from the other one, I think this is way too yeah, maybe this is way too complicated, because then now we don't even need, I mean, the total delta stuff is nice, but maybe we can, let me double check whether this is, when am I lying on that? But we can actually just go, yeah, given the new median, we can just choose, we can divide the thing into two, right? So that means that we can do two queries instead, right? We can go from negative infinity, which in this case is actually a million, which is kind of awkward. I need to put this in a variable, to to m, right? So this query should be the same as left sum, right? So that's why. So then maybe new cost is you go to, this is the left sum, right? And actually, maybe I'll just be a little bit lazy and copy this here, right? So m is the new median, right? So yeah, so this is the left sum. So we have m times the number of things on the left, which will always be size divided by 2, right? Yeah, round up, right? And also new cost, right? The right sum is just from m to our infinity, which is there, minus median times right? So that would be it in theory, and then we could even bring back this audit, right? So basically, the audit should have the last 3 numbers the same if everything goes right. Okay, it is not though. I think it's roughly right. I think I'm not. Maybe I'm off by 1 on the left right thing. But why is it off? But yeah, you're free to kind of skip this part, and you can watch me live if you really want to. I am gonna try to upsolve this, even though it's almost 6 a.m. and maybe it's time for me to go for a run. But and try to, it's not an upsolve, it's just trying to understand, because maybe this is another way of solving it. But yeah, oh, maybe I just can't do m. Yeah, wait. Also, what is this m? The right sum? No, that's fine. But I think this is m plus 1, maybe? Maybe I'm double counting m, that's why. But I don't think that matters. Yeah, okay, actually it does. Oh, I mean, this one is wrong, but it got more of it right. So I think there's some stuff about... yeah, maybe there's some stuff about off by 1 or something. If they're even... or maybe if this is m minus 1, maybe? I don't know. I mean, that shouldn't matter, right? Because in the sense that it would have subtracted them out, maybe? But, that's right. Does this do anything? No, that is necessary as well. Why am I off by 1? Am I doing this wrong? That's just wrong. And here, oops, are we double counting it? So this is Yeah, everything is -2. So why is this 4? I mean, this should be... Alright, I guess I could just print it. This is left sum. And this is right sum. Okay. Okay, so yeah, it thinks the left sum is -4 because it includes this as -2. So okay, so size is 3, so that means 2 on the left, 1 on the right. But I think that, yeah, I think the idea works, but versus this, but because of the tie breaking rules, I think that's the tricky thing of yeah, maybe that's fine. Maybe I need something like this actually, but the size is... But yeah, okay. Actually, I think this is fine. It's just that we have to do another binary search, so it's not... Right, so here we do median dot bisect left of m, maybe. That's the number of numbers that are m or smaller. And then here... Because the count is not fixed because of the tie breaking thing. Or if multiple numbers are the same. So now this is bisect right of m, but n minus this, or size minus this. Okay, I think that's why. Okay, maybe not. Bisect right. Am I missing by 1 or something? Nope. Why is this wrong? This part should be... Okay, so number of numbers that are smaller. Oh. This is very awkward. At some point, the parents went the wrong way. I think auto parents kind of corrupt that one for me. Yeah, there you go. And you can see that now, yeah, given this is the rewrite of what we had. And then now we can write cost of left is equal to new cost. And we don't even, well, okay, we'll keep the audit here. But as a result, we don't even need the last median anymore. So that means that we are able to get rid of all this complexity. Actually, yeah, and get rid of all this maybe, and then as a result we don't have to keep track of total delta anymore, right? Or last median, right? And then we click submit. It may still be timeout because this one timed out before, right? Because of the sparse tree or sparse segment tree, but yeah, we'll see if it's... It should be faster, just because there are fewer things it's doing. But at the very least, the yeah, that's fine. Oops. Yeah, I mean it's actually maybe slightly faster, but and did not make a difference. But you can see that it oops, not that. I guess I have to submit again to get the wrong answer. But yeah, I mean you can see that it did like 98%, 99% of the thing, so it's close enough, but it's not fast enough. But at least now the code is much cleaner, right? So you know, sometimes learning is about doing crazy things, and maybe this idea will come in handy in the future. With this one, it did not. But anyway, yeah, that's what I have with this one. Let me know what you think. Thanks for watching, and yeah, you can watch me solve it live in the contest now. My idea, even if I don't have a good idea, let's skip ahead. And the integer nums to integer x and k. Increase any element by okay. Return the minimum number operation to have at least k non-overlapping subarray of size exactly x in nums where each element are equal. Okay. At least k non. Okay. Constraints are pretty. Ooh, k is 15 is interesting. Maybe what's k again? Okay, so we want 15 overlapping things maybe, and x is pretty big. So okay, what is x again? Oh, size of exactly x. Okay. Is it just sliding window type thing or? Okay, so we want to prefix sum. I think that's straightforward, so that we can get the total of the rectangle. Okay, let's just start with that. Okay, so now we have to prefix sum, and it seems pretty straightforward. Maybe not. It's 15 times n. 15 times n should be fast enough, right? So yeah, okay. I think this is actually pretty. Oh wait, no. So okay, so that means the two things, right? So let's say we started with current index. What does that mean? Well, we have an ideal thing, right? And the sub thing, it's going to be. So you have all these points. How do we make it exactly equal? I guess it's median. Yeah, median makes sense. So rolling median. Rolling median is annoying but doable. I have code for it somewhere. Rolling median for okay, fine. Okay, fine. That's not so bad. Let me see if I can find my code for it. Actually. Because it's just 2 heaps, right? So we do for each heap, so that's log n, and then we just do another 15. Okay, yeah, maybe that's fine. Where is it? Okay, I don't know where it is. But alright, let's just say x elements. Okay, that's fine. So maybe yeah, okay. And self.left. Right, so left side is going to be, the top is going to be max heap, right? Yeah, okay. Max heap, min heap, and okay. That's it, right? Maybe. Well, update and remove. Okay, how do people probably have copy and paste for this, but yeah, okay. Yeah, okay. X, right? And yeah, okay. Yeah. And then solve that balance or something, maybe. Oh. How do we do a lazy removal? This is actually more annoying than I thought or remembered. Is there any other way to do rolling median? I think this is roughly right, but I have to forget that the removal part. Let me see if I can find my code. Okay. Found something. I don't know where I got this one, but okay. This is the same idea. Hopefully that's right. So then now we go. This is also terrible that let's go to size. Right, X is the size. Yup. Nums. What's K again? K is the minimum number of things. Okay. So then. Rolling median. Right. Now for X and nums we go. Yeah. Okay. Is there median dot size? Median dot count. Okay. Okay. I don't know if I need this, but I think that's easier. I don't know, maybe not. No, left is yeah, okay. Right. If right minus size greater than equal to 0. Is it remove or delete? Remove. Okay. Let's see if that works. What is add and slide? Why do I have so many things? I don't know why this is here. Okay, so it's 5, 1.4. The size is going to be 3, so this should be 1. This should be. The size is 3, right? So the answer shouldn't be 1, and then this should be. That's not right, is it? This code is just not right. I don't know what I was doing before, but maybe I haven't done a rolling one. But there should be 1. So this is 1, this is 1, and then this is 3. That's not looking good, frankly. Okay, let's take a look at the code. I mean, it has most of what I want, maybe. So I don't know what this add-in slide is. It's like lead library or something. So this is 2, this is 3. Okay. So then why is it giving me 2.0 even? Would be here. But right? So it's 2 and 5. Okay. So then this is the max heap. It would just be 2, right? Why is it giving me? Oh no, it should be just 1. Okay, that's fine. Oh, but it's not subtracting. Am I off by 1 on size? Off by a lot on size. We don't keep track of window size at all. Did my was that in there? In the report that I took out? No. What the? And but this lies, right? Even though the count is. But we don't remove it from the. Oh, I mean, these are lazy removals, which is fine, but then it means that this is not quite right, right? Yeah, it's not correct. What was I doing? Is this white code line? Let me just ask ChatGPT. Maybe it knows a little bit better. I don't care about this. Okay. Of course. Oh. Okay, is this now right? I do want to multiply 2 by the median, but maybe that's fine. There's all this Q stuff anyway. In any case, is this now right? 3 elements is 1, 2. Nope, 2 is not right. And what is going on here? I'm spending more time on this than anything. Okay. Is there another way without rolling median? Let me just Google for an answer. I mean, not the answer, just like I feel like there's a pandas thing for this. That's why. Does that work? Do I have pandas? I'm curious. Okay, there's no pandas. That would have been actually interesting. But what am I talking about? I'm being dumb. I could just use whatchamacallit. What is that collection cost? I am dumb. Why am I blanking out on the collection name? It's the one that everyone hates. Sorted list. I am just so rusty. I don't know why. And I thought I had code for this, and I didn't want the medium, so maybe that's fine. Okay, right. And we don't care if it's even number. We don't care which one we use, so that's fine. Actually, so okay, left is equal to right minus good. that right? No. That's why this is awkward, but that's fine. I want to be precise so that I can write. This is the size. If this is okay, we can also just do if length of median is equal to k, the size, then, and that should be the variant. Then here we print median of length median over 2, right? And that's good. Okay, man, I'm so dumb today. Sorted list. Take this. Okay, there you go. Is it right though? This is 1. I don't know why I struggle so much on that. That's I was talking about being slow, and I am definitely slow as a result. Okay, so that's fine. Okay, and then now with the prefix sum, right? So okay. Okay, so then now we okay, now we have the median is equal to this thing, right? And this should be size anyway. Okay, so this is the median. So then the size am I getting that wrong? Wait, maybe. Okay, so we want the okay, so difference. The problem is that oh no, am I thinking about this way? How much time do I have? So here we have to but it's the sum of the deltas, right, around the median. Is that right? Man, I focused so long on the median. I mean, median is going to be the right one, but we still have to figure out how to do the thing, right? Okay, so we have median. We want to sum up all the absolute values of the number to the median. How do I do that? I just thought I could do the area trick, but that's maybe not right. Because if you have 0 and 10, the median would be 5, say. And the area doesn't make sense, right? So I'm thinking of the average. The area is an average thing, isn't it? Huh. Man, I'm just struggling this one. Okay, so we know we want to turn the median. I need to draw some stuff out. Okay, so let's say you have 1 and 9 and say 3, so the median is 3. How do you get the sum of all these things? How do you chop them off in a good math kind of way? You do it once and then you calculate the delta. You know how many numbers are smaller than that? Okay, fine. That's just annoying, but it's doable. I think just on the delta, right? Okay, so this is the median, right? Okay. Let's just say mass thing is equal to none. Okay, then here we want, okay, so then here the total delta, actually do it here, and then we go from for x in sorted list. Where's my sorted list median? We want to say x minus median. Okay, so then now that's the total delta. So that's the cost, right? Alright, maybe we need an abstraction. So cost is equal to none times n, and this is on the right side. Maybe we'll shift it on the left side, but maybe that's fine actually, but whatever. Okay, so then now we have the left, so cost of left is equal to total delta, right? And we're happy, and last median is equal to m, maybe. Otherwise, okay, so we know that by definition, okay, so by definition, that means that this, okay, smaller is equal to smaller, or, well, okay, so maybe the two. Okay, so how do it's case analysis is easy. I think easier than the other thing. Okay, so if last median, then nothing changes, maybe. We also have to take account that we moved and add some numbers, so that's really tricky. Okay, do it for the first time. Okay, so we add a number and then we remove the number. Okay, so then if last median is not none, then num sub right, or absolute value of this minus m, or last median, we want to add it, and here we want to subtract it, right? Because we pop and we put, and then now we have to get the delta, right? Okay, then nothing happens, right? Okay, else if m is greater than last median, then yeah, median dot bisect left, and it should always find it anyway. Of so how many numbers are okay? So how many numbers are okay, if m is greater than last median, so okay, so the three sets of numbers, so the count of numbers that are bigger than left, m, right? So here we have median dot bisect left of m, actually right, so it's all the numbers bigger than it, right? And in those cases, they all subtract, right? So this gives me the index. So this, the count is going to be the size minus this. Maybe I'm off by 1. Okay. And then smallest is going to be median dot bisect left of m, is it? No, of last median. And that's the number here. And the biggest, so total cost of all the big numbers is gonna, it goes from L to M, so it gets smaller by, median minus last median times the number, so biggest, and then smallest, it gets, oh no, this is subtract. Yeah, okay, fine. And then the stuff in the middle. How do I get this stuff in the middle? So that's x. So the stuff in the middle, we have the total, and then we have to invert it. So it's going to be last m minus last median. So the area is going to be this minus the existing delta, right? How do I get the existing delta? How many numbers are there? Existing is the sum of all the numbers that. Am I doing this right at all? Man, I just don't know how to solve Leetcode anymore. Okay, so that's the whole area. But what was the number before though? Maybe I don't know this one. Maybe I should have thought this one first. Man, I'm just not solving anything today. Or these days anyway. M minus last median times, okay, so that's area. It's the sum of those numbers, but we don't keep track of it anywhere in a good way. And I don't know that I can add to keep track, so maybe I'm just wrong. Okay, let's reset for a second. And once we have that, the DP is easy, but but it's just about getting the median, and I mean the median is fine, and it's just calculating out the difference, right? Maybe I'm just wrong. Can I calculate it from anywhere else? How do I even? Can I calculate it any other way? And x could be pretty big. So I can just do like another loop. Okay, maybe this is not the way to do it. The actual DP is straightforward, but do I need the median? Yeah, I mean, that is for each component. Sliding window median is fine, but the total delta of the median is weird. Is there a different way of writing that? I thought that I could do a quick math, but I was wrong on it. I did the math wrong in my head with respect to the visualization. I don't know how to do without another loop. That's the problem. Like maybe with another loop I could do it, but everything else it just would be the same way. So maybe I have to do another thing. And the sort of list for median makes sense. First, 6 minutes. I mean, that's just ChatGPT, I guess, but or 2 minutes even. Reasonable people maybe got it already though. Still, like Dylan Smith, 15 minutes. I thought I could maybe flip it, but I don't even know the sum of the area of the numbers that are within that area. Do I need like another data structure for it? Can I do a sig tree? Everything is sig tree, but what would that even look like? So you have a thing. It goes to 10 to the 6, so can we do a sig tree on that? But that's what you would want to do. Add an element. And for each element, you have to change it, right? I don't get it. Oh no, you. This one you could do with the sum and do it with math. Actually, unlike the median one. Because here now you're just getting, okay, so you have the area. Okay, let's see if I have a sig tree then. Fine. So basically we want to add I mean, okay, I don't know if this works. I don't know. Maybe Leetcode is, I mean, ChatGPT is useless for this. In terms of segment tree. How much time do I have left? 40 minutes. Yeah, okay. Maybe I can implement it myself. No, but it's sparse. Right. And each node would have no, this is range, right? Something like this, right? And then yeah, and then now we have self dot is equal to node of, was it, negative 10 to the 6. Okay, right. And then we want to implement increment. Then we could do it iteratively, right? So kind of if key is okay, yeah. We're going to write it this way. I don't know if this is better. Right, and then now this means that the current node would be pretty Gucci, right? That's why people implement this recursively, but yeah, whatever, let's just add a parent, I'm lazy. Okay, and then now current.count increment by 1. left is equal to right, and then while current is not equal to self.root. Something like this, right? People talk about sec trees. I could do sec tree. All right. There may be 0 though, so that's why, or there may be no. When there's a no thingy. Right? Yeah, okay. Still have no idea how to do Q3 though, honestly. Okay. And then we are done. I think. Same thing, really. I guess actually we should just add a delta. Okay, but then now we want to query, which is left, right, right? How do we write this? So then now, yeah, left. We want the sum of a lot of things, right? So, okay. Can I do it this way? The numbers should always be existing, so I don't have to check for this actually. So if this is on the left side, okay, say you have what am I checking for? This is actually very awkward. This part I don't know how to do. I mean I know how to do, but so that's your search range. Or at least I don't know how to do it iteratively, maybe. Maybe recursively is fine. But alright, let's just do it recursively then. Yes. Current left, current right as the current node, right? I mean, it's just tricky to get it quite correctly, but I think we need a. Okay, so now we're outside. If L yeah. Otherwise, okay, we'll left some. But the problem is that the way that I'm running it now, maybe not. No, I mean, yeah, maybe this should be fine. I don't know. Should not be that bad. Should be just log in, but maybe it is. I don't know. I haven't run this in so long. Okay, so now I don't even know if this is right. I mean, okay, and then now we can query for between last median and M, right? I guess I need a helper. Does it not crash? That's the first thing I want to see. An infinite loop. Maybe it does because I think I memory limited. That just means that yeah, maybe something here is weird. It should not be this one though, because it must be here. Right, let's take out the query for a second. Increment should run out of things to call. Why? Did I get this wrong? Oh, I don't update left and right. Okay, so then okay. And none. that count and left. Where is that? 36. That doesn't even make sense. Count. Oh no, left value. Okay, left value should not be 0 though. If we do fill it in. Oh, we don't fill it in. I lied. Very inconsistent. Okay, so it does something, which is nice. So then, yeah, area minus. Okay, so this is the sum. So this is the thing. They're all bigger than median, so I think I can just do this, actually. And then probably not right. We cannot have negative costs, so this is definitely not right. Median. Oh, okay. Let's see. Going from don't even have time. How much? 23 minutes. And sorted this. What I call it? Median for some reason. Okay, so here we went from 1 to 4. So the query for 1 to 3 enters 4 is right. Last median. Now we have to update last median also. Okay. We'll have to do some other stuff about the other direction, but I need to see this first. Okay, so 3 to 1, we have 4. Okay, that's fine, maybe. 3 to 6. So the previous sum should have been 9 here. I don't know if I do the other things correctly because. Okay, fine. I guess we have to write it out. I think it's mostly the same though, except for okay. Right. This part could actually be the same. Maybe it's wrong, but. Sort of list on line 51. I pass in a sorted list. Oh, whoops. I do pass in a sorted list. Should print a lot actually. I don't know why this is not printing. Oh, the median doesn't change. Okay, fine. The cost still should not be negative, so something is very wrong here. Okay, what should be the ideal thing here? All right, so you have 137. Okay, so for x and median. Okay, so that's already not great. Right. Seven and 5, so 7 is a cost of 521, maybe. Okay, so we move to 1, so this is 3, this is 3, this is 3, this is 2. Audit should be 2, yep. I mean 5, sorry. 7 is definitely way wrong. Which path does it go? Not here for the first time, so that's okay. Because now you went from this, the median went from the median went from 1 to 1, so that means that we're doing here. That's wonky. Okay, so this is 7. This is 4 plus 3 is 7. So then why did it not get updated here? Okay, so it goes to 9 because the median is 3, and then because I am an idiot. Okay, so this audit passed, but this one does not, so okay. That's fine, the delta actually changed here. Right, so median is, it went from 1 to 5, so we have here. That means this thing should have kicked off. So the median is that. Going from 1 to 3 should have given me a total of 4. Okay, I mean that sounds right. Is this right? Median is, so that's 3 times, okay, maybe middle as well. No, this is 2. Right? Yeah. So this is 2. 2 times m would be 6. Six minus 4 would be 2, so delta should have gone up by 2, right? The previous delta is 5. Did I do the order of operation right, maybe? So we removed this number, so maybe that's why. So we up. So ordered is wrong, but this is wrong too. I can't solve anything these days. Maybe I gotta quit. This is 4, this is 2. That's, yeah. Okay, so this is 4, this is 6, so this is plus 2, right? So the total delta, which one is ordered? Ordered. Okay, the 6 is the ordered, so 6 is the right amount, but the 8 is not. Am I double counting? How many numbers are... 0 numbers are smaller than 1, which is true. 1 number is bigger than also true, unless I did those math wrong. And so the biggest is 1 times delta, so minus 2. So the total delta went from 5 to 3. 3, this is 0. 3 plus 2 is 5, right? Am I? Okay, so the total delta is 8. Oh, because I do some changes here on the last median, which is fine, right? Okay, so we move the -2 with the median being 1, so that's plus 3, so went to 8. Right, and then we subtracted 7 to 2, so that's 3, right? Yeah. Okay, I don't know anymore. So 5, 8, that sounds expected. Okay, right, so went from 5, 8 is, yeah, so it -2 and 1, so it moves 3, and then 2, and then 7 and 1 is 8. Okay, so we have 8. Okay, that checks out, maybe. Right, so then 8, moving from 1 to 3. So 2 numbers get flipped to 3, and it costs 2, which is what we expect, which is what we get from 4 minus 2. So it would go to 10, and 1 number got smaller, So one number got smaller by 2, so it should still be 8. How is, but 6 is the right answer because it's 4 plus 2. This is like one of those silly brain teaser things where I'm really bad at. About 10 minutes we're not solving this. I'm just like really bad these days, apparently. I mean, it does everything I want it to do, but why is it wrong? So that's based off 1. Why is that wrong? Because the line is at 1. We move to 2. Subtract by, so it's 2, and then but we add back 6. Right, with the line being at 1, okay. Now we move the line to 3. Is the 8 right? 8 is the distance 2 plus 6, so 8 is right. But moving from the line from 1 to 3 is wrong. 2 numbers subtract, so that's... Oh, is this... Did I have the signs wrong? Maybe. Okay. Well... So the area is... Okay, so the stuff in the middle, maybe that's why I'm... Okay, so you have... To get the area... It's not a delta. I think that's the problem. I think this is, well, we don't add subtract. It's a replace. Right? So this gives us, but we have to subtract from something else, which is I see. So we add the thing. Okay, so that's added. So the subtract is actually equal to okay, that is, how did I get that math wrong? And we should pre-cache that anyway, but okay. I mean, here we probably have to do the same for this one, which is why. Okay, this order is still wrong. Maybe the signs are still wrong. I don't know anymore. What is this? Why is this that wrong? I mean, it's probably just that this part is wrong altogether. I kind of just got a little bit lazy about it. Let's get rid of this for a second. What does that look like? Negative 28. So I went from M. Okay, so that's still in this part actually. So and everything checks out before that. So okay, so if it's still in this part, maybe. Why am I so bad at getting things right in the first time? Okay. 7 going to 25 is nuts. No, 25 is the correct answer, so we're missing a lot. And maybe just, no. This is the ordered. 4 is the right answer. I don't even remember what are these things we're printing are for. Oh, that's the sum. 25 doesn't sound right. Between 3 and 6. Yeah, 25 is definitely not right. So I think my segment tree is wrong. Is why. I mean, there's not 25 in here. So did we decrement it incorrectly? Yep. Okay, so I think this is finally getting to the point where this is wrong, which is good because we've been waiting for this. Because we need to debug it. 4.6 for the first time. Okay, so it's smaller. I have to audit this. I thought this would be, this makes more sense, but still not right though. I hate that I have to debug so hard. At least we got the other ones right, but what am I printing here? Okay, so now we can see that all the audit works. I guess I didn't have to mess up the signs. I have 3 minutes, so took me long enough. I'll probably finish it, but not in time, unfortunately. So then now it would just be, yeah, now we could do the DP, right? Smaller on the outside, is it? Yes. Minimum number of operations, so let's just say infinity. Exactly K or at least K? Well, I mean, you're not going to do more than K, so it doesn't make sense. Okay, fine. Right. And now for... okay. Okay, so then J is equal to or if I minus the X or size, did I rename the size? Okay, so it's this plus cost of left, which is I minus size. And that's it, right? Is it always possible? It is. It should be always possible. So. Huh? Oh. Whatever. We already said it. I guess it needs to be that anyway, but I feel like I'm off by one somewhere. What? Oh, I forgot that I usually write it this way, but I actually want it the other way. Okay, that's. This is now confusing as. Well, not going to finish on time, but I guess that's okay. If we finish, it'll be okay. Yep, just finished. I mean, time-wise, just finished. We didn't. Huh. Oh, yeah, again. This feels more unnatural to me. Okay, that's not great, of course. Let's see if it actually does anything. Nope. Do I get costs right at least? Maybe. Okay, so cost should be right. Am I off by one? This is the only thing with none, so. Okay. What a disaster. Doesn't need to be n+1, does it? Okay. Yeah, okay. But why is it not getting anything? Yeah, this actually makes it annoying to write. That means that nothing is hitting the 0, 0. Not even the 0, 0. Well, J has to be 1 anyway. I think I overwrote it by accident. There you go. No, it's max of this. Nope. No, it should be though. Why not? I get the index one again? No. This is right. Why is this not giving me? I mean, even if it's giving me the wrong answer, it should give me the wrong answer. Why is it giving me 10,000? Oh, I don't want max, I want min. How am I so dumb? And also we... that's wrong. Okay, that's fine. Because I forget... No, this should be... Right, this is wrong. That's why. Okay. It's not right, but that's fine. What is x2? I think maybe I'm off by 1 or something. Right, so if it's 2... Oh, what's k is 2, so x is 3. That means that we want 2 of these numbers. How do you get 8? Did I do this wrong all the entire time? Okay, so what is the cost here, right? The cost is going to be 3 to nums 1, so 5. There should be a 5 in here, right? Okay, that's 5. That is fine. Okay, this is of indexes. This is k of 3. Okay, let's actually now print the DP. Okay, so 0 is fine. This is 7, but they should all be zeros. That's why. Yeah, I just had the wrong thing before. Okay. That's a little bit better. All zeros. Yeah, because it costs 0 to do it. There's 5 here, that's fine. And then... How did I get 7? 7 is because there's a 4. 4 plus 3 maybe? Am I off by 1? Maybe I'm off by 1, that's why. On the sizes. That one I wasn't sure about. Okay. I don't know if this is too slow, but at this point just YOLO. It may be too slow, frankly, because of the stick tree and stuff. I'm not quite sure, but at least the idea is right. Maybe we'll cheat a little bit afterwards to figure it out. I mean, complexity-wise, this is fine, but but maybe I'm wrong. Hang on. I mean, this seems like a margin thing, and not because my algo is wrong. So I'm not really worried about it per se. Like 18 on one move, so yeah, this size is 0 to 1. J. We'll just do. I don't know. It's confusing, sorry. Okay, so now we've put this out with 0, that's fine. But here, why is it not tracking? Size is 2. Might have been off by 1 somewhere. Size is 2. So that means, yeah, this is weird. I think I'm just off by 1 somewhere. I think that's the more correct one, but maybe my costs are wrong. Left is should be inclusive, but maybe I'm wrong on that one. Maybe I need to do this is kind of annoying actually. That okay, so this is 2, so there shouldn't be any element here, so this is definitely off by 1 somewhere, right? So actually, no, the other one was right then. Is that true? Yeah, I think so. Man, I can't believe I'm doing it off by 1. Yeah, okay, so 2 because it offsets from here. I think this is more correct, but what I need as a result is that, okay, so I do need an I plus 1 thing, that's why. There you go. Silly Larry. Come on, baby. If it times out, maybe I'll cheat. I look at the leaderboard, I mean. Oh. Oh. Well, I mean, that's just not a high enough max, which is... maybe I just didn't do the math. I mean, I definitely did not do the math. I usually do 10 to 20, but the reason why I wanted to try something smaller is because I thought that initializing this would double the size from a long to a slightly bigger long, I guess. But yeah, and that might come in. I actually don't know if that's as a result of this. So let's see. We'll try one more time, but we'll see how this. Well, yeah, we'll see how this performs first. Maybe not. Maybe it doesn't matter. I mean, 3 seconds. Maybe that's a little bit long anyway. Let's YOLO submit because we already not gotten it. But okay, so it times out. A couple things we can do maybe before we start cheating. I mean, yeah, I don't know. It's not great. I think this is a moral victory, but yeah, right. I just wanted to get a benchmark time, 8 seconds. Let's just say I mean, you should be able to combine these, but I don't know. I am apparently a degenerate. But I don't know. I mean, yeah, it doesn't change too much. I think using a sparse segment tree was always going to be a little bit expensive. Even though it is n log n, everything is n log n, but apparently not fast enough. Because this gets denormalized, but having a node is not great. Maybe we can besides, oh yeah, we can just use a stack. Okay. Okay, so then now, it's not return anymore. Oh, yeah, this we can just continue. This redo result. Continue. Otherwise, yeah, we just push. I don't know if this is that much faster, but hopefully. And hopefully we'll get something right. Where's my segment tree thing? Yeah, it's slightly faster, but it's not going to be fast enough, right? How many? Yeah, we're so close. Alright, YOLO submit then. I don't think it's good enough, but we'll see. Yeah. It is very frustrating to be so close. But a sparse segment tree isn't something that people normally do, so I don't know that. Like, I don't think I would consider it like an optimization thing. It's just me being. Can I simulate something like this? I don't know that I can usually. Is it like I'm trying to think whether there is a replacement for this. I mean, okay. Maybe we have to do without the nodes. We just have to do some really crazy renormalizing type thing, right? Yeah, but that is such a annoying optimization to do. But it makes our storage better, which in terms should be faster, but I'm not convinced, honestly. Let me take a quick peek to see if it's a segment tree thing. If it is, then okay, there is some heap things. The DP makes sense. I don't know what the M costs, unless this is max flow. So it is on the sliding median. So the sliding median can get the cost by itself, I guess. I mean, that would have been a lot easier instead of all these crazy things, right? Let's try that. That seems reasonable. I mean, I was thinking about it that way, but it's hard to tell which what thing to use and what not, right? So, all right, let me open a new window actually. But I think the way that I want to, the way I want to rewrite it, unless last time, is that I'm not going to use a heap, but I'm going to use two thingies, right? So that'll be a little bit easier. Yeah. Right. So size maybe. So this would make it easier because it was too hard to keep track, but I forgot sorted list for some reason. So okay, so then now we have cost 0, 0, right? Okay, so what does add look like? So up that left. Okay, we just have to keep track, I think. Yeah. Read that, right? Because we know that it exists. Okay. Okay, yeah, let's do it this way. Then now okay, so if length of is the cost of 0, 0, none. Oh. Just put everything on the add side. Otherwise, because there'll be also have no removal by definition. Otherwise, then now we balance for the first time. Okay. Otherwise, then now everything is balanced, so we want to add that's nothing, I guess. Okay, so let's just say we have that. We don't have this anymore. We have maybe I don't need an add and remove. This remove is awkward because we're doing this anyway, so we might as well just have a different remove. And then we don't need the cost. It'll just be what we return anyway. Okay. Okay. Then now this is median.add and there's this sorted list. Do I need sorted list anymore? No, this does it for us, right? So actually, in theory, I should be able to write this. We don't care about this anymore. We don't care about this anymore. We don't care about this anymore. We increment. We don't care about this anymore. Decrement. We don't care about this anymore. This is not quite right, but yeah, I don't know what that is. And it's just cost, right? So cost sub left is equal to median dot cost, and then that's it. This doesn't do anything yet, but it's fine. Median has a size, and the size is just... I still haven't even tried Q4 yet. Huh, do I rename this? Need more water. Okay, I'll do this. Okay. So then now let's say, okay, then we just do it for the first time, right? So here, what's the invariant? Invariant is that self.left is going to be less than length of self.right. Right, so while length self.left is greater than length of self.right directly because of the Leetcode, then that's fine too. Then, yeah, then we remove the biggest number. And then we add it to the right. Okay. And then now cost would be, well, now it's easy to do the sum to the left. Right. Why did I do this twice? I guess we always do this anyway. Okay. And then now, okay, so now what do we do with cost? If cost is none, then we just that's only okay. So then we get, just to keep it easy, I think. And the median is this thing. This is self.cost. Oh, yeah, no, we're already done. And then we return, and that's it. That's just to kick it off. Right? See if it crashes or anything. Okay. Okay. I don't know what this is, but it should be fine. We don't do anything. We just set it once and then we don't do anything, right? So cost is over 10 because For the first time it is 10, is that right? 4 plus 3, it should be 7. Oh, I see, because my invariant is wrong. So if this is the case, yeah, we want the extra ones to be there. Okay, I think this is fine. Okay, and then after that, it is balancing time. Okay, so we add a number first. I mean, I guess it shouldn't matter, but we add a number. So we add a number, that means that by definition, we add it to the left. So that means that we do this thing again, right? Only difference is that, so we pop this. So that means that we go from, in this case, it would go from, we put in a 3, the 3 would be here. But that wasn't the median though, right? I guess maybe I'll just keep track of the median, maybe it doesn't make sense. Okay, right. And then now, whenever we add, I want to say left sum. Maybe this thing doesn't, oh, I did here, doesn't make sense. Maybe we just need to do it incrementally. No, I don't want to do it that way though. Okay. Right. All right. So far, so good. Maybe. All right. Let's keep it. Keep. Okay. Oh, that's actually. It's not the right answer, but it's interesting actually. Okay. But we still gotta balance. We have to change the median. That's why. Okay, yeah, fine. Okay, so here we want to move. So we have the old median, right? So here we say, okay, so we want to remove from the left. want to put on the right. I guess we didn't need to do this part. We'll leave it in for now. And then now we have to shift the median from, okay, so delta is equal to median minus okay, and all the numbers that are smaller, which is on the left side, you're trying to go to so we have left sum. It's going to be delta is the new median, so nope. What are you doing, Larry? It's delta times the number of numbers minus the left sum. Yep, because we want to bring it to the median. No. This is the new median. Okay, we have to do it again. So the delta is going to be this, right? Actually, do I need to? Can I just set it? We know what the new median is, and we know this left, right? So new median times length of self.left minus left sum is the thing, and then the right. So that's to bring it up to that level, and then on the right, you have to try to bring it down. So that's just sum minus, okay, yeah, actually I don't even need that. I don't even have to keep track of the cost, do I? That's not so bad, right? Do I have to keep track of the costs? Maybe I'm nuts. Okay. Anyway, while self.right is greater than length of self.left. So if they're equal, then we don't do anything with greater than. We do want to bring it. Okay, yeah. Why am I so bad? I should have been able to get this. I didn't have sortless. Not that I didn't have it, it's just I wasn't thinking about it. You don't even need the soft medium, right? This is all I need. You don't even need this, the way that I think about it. Okay, I mean that's not great. Maybe I'm wrong. Alright, so this is my old code. I just wanted to print out the cost for the example cases. I could at least have comparison. Why do I have -3? Is it just me being nuts, or? Let's see, the right side, the new median, How can it be negative? Dum, dum. So 1 and -2. The median is 1. Huh, how did I get a -2 on the other side? Oh, I rebalanced incorrectly. Because I always, when I add, that's fine. But when I subtract, when I remove, that's not fine, right? Am I doing this wrong? How come? Okay, 9. Add a -2, -2. This is fine. Negative is fine. This is. Are there 3 -2s in this one? There is actually. Okay, fine. Subtract. Add a 1. Oh, that's where I did it wrong. I should have added the 1 to the right side. I guess I was just lazy. That was my convention usually, but okay. So then now, if add is greater than if length of self.left is none, or and then do this, right? Else if self.left of -1, the biggest number, is more than okay, and then else we just do on the side. I feel like I make this mistake every time for some reason. I'm just like, for some reason I like, even with the heap version, I think there's an invariant that I didn't know about. But okay, this is still wrong, but that's okay. I just means, so the add is, oh, I did it the other way. Whoops. Okay. Do I have a weird case? Okay, this is a weird enough case for me to test. So, okay. I thought that might happen, but I didn't think it would happen so fast, honestly. Okay. Click submit. I mean, if this time's out, then I don't know what to do. I mean, maybe give me a wrong answer and that's fine. But okay. Yeah, okay. Honestly, not super bad, but I'm not super good either, clearly. It took a long time. How long did that one take? I don't even know anymore. I mean, I'm beyond an hour in. I have a screenshot though. I didn't take that much on Q3, so this took like a long time. But I solved it in 2 different ways, so I should have done it this way, but I don't have a library for it. But well, maybe this is my library in the future. Okay, so let's see if I can upsolve. Thanks for watching, everybody. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about this contest, this problem, this explanation, everything in between. Stay good, stay healthy to good mental health. I'll see y'all later and take care. Bye bye.